Welcome to our coding walkthrough. Today, we'll be tackling LeetCode problem number 334, increasing triplet subsequence. This is a fascinating problem that requires identifying whether a given array contains an increasing triplet subsequence. We'll explore different approaches and analyze their complexities. Let's dive in. In this problem, you are given an integer array called nums, and the goal is to determine whether there exists an increasing triplet subsequence within this array. This means we are looking for three indices I, j, and k such that I comes before j, and j comes before k, while the values at these indices follow the condition nums, I, nums, j, nums, k. If such a triplet exists, we return true, otherwise, we return false. Additionally, the problem has some constraints on performance. The solution must work in linear time, or O(n), meaning we can't afford to use nested loops or other approaches with higher time complexity. It must also use constant extra space, or O(1), which means we can't rely on auxiliary data structures to store intermediate results. To better understand the problem, let's look at the input and output format alongside some examples. The input is an array of integers called nums, where the length of nums is guaranteed to be at least 1 and at most 500,000. Each integer within the array falls within the range of -2 billion to +2 billion. The output is a Boolean value, either true or false. For example, consider the array nums equals 1, 2, 3, 4, 5. Here, the output is true because there exists an increasing triplet subsequence, specifically 1, 2, 3. This sequence satisfies the condition since the indices of these numbers follow the order I equals 0, j equals 1, and k equals 2, and their values are strictly increasing. By contrast, if the input is nums equals 5, 4, 3, 2, 1, the output is false, as no such increasing subsequence exists in this strictly decreasing array. Now let's examine one more example to illustrate the problem in more detail. Consider the input nums equals 2, 1, 5, 0, 4, 6. Here, the output is true because there exists an increasing triplet subsequence 1, 4, 6. These values satisfy the condition nums, I, nums, j, nums, k, with I equals 1, j equals 4, and k equals 5. Notice that the indices of the triplet do not have to be consecutive, they only need to maintain the correct order. This example highlights that the triplet can be scattered across the array, as long as the relative order of the indices and the increasing value condition are both met. Finally, we need to consider the constraints and edge cases for this problem. The constraints specify that the array length can range from 1 to 500,000, and the values in the array are bounded between -2 billion and +2 billion. For edge cases, if the array length is 1 or 2, it is impossible to have a triplet subsequence, so the output must always be false. For large inputs close to the upper limit of 500,000 elements, the solution must be efficient enough to handle this size within the given time and space complexity. Duplicate values in the array do not affect the validity of a triplet, as long as the condition nums, I, nums, j, nums, k, is satisfied. Lastly, the algorithm should also work seamlessly with negative values, as they are allowed within the constraints. These considerations ensure the solution is robust and handles a wide variety of inputs effectively. To solve the increasing triplet subsequence problem, we can consider several approaches, starting with the brute force method. This approach is quite straightforward. We examine all possible triplets of indices in the array and check if they satisfy the conditions for an increasing triplet. Specifically, for indices I, j, and k, we ensure that I is less than j, j is less than k, and the corresponding values at these indices form an increasing sequence. Implementing this involves using 3 nested loops to iterate over every possible combination of 3 indices. While this method guarantees correctness, it is highly inefficient for large inputs due to its cubic time complexity, O(n cubed), which arises from the 3 levels of iteration. On the positive side, it doesn't require any additional space, as it operates in constant space, O(1). However, this inefficiency makes it impractical for larger arrays, which is why we need to consider alternative solutions. Another option we explored is an optimized approach using dynamic programming. A more efficient strategy involves dynamic programming, aiming to reduce the problem to finding the smallest increasing subsequence of length 3. Here, we use an auxiliary array, dp, where each element dp, I, stores the length of the longest increasing subsequence ending at index I. For each element in the array, we compare it with all preceding elements to update dp I accordingly. If dp I ever reaches a value of 3, we immediately know an increasing triplet exists. This approach significantly improves on brute force, as it reduces the time complexity to O(n) squared, by eliminating one layer of nested loops. However, it still requires O(n) additional space for the dp array, making it less efficient for very large inputs. While dynamic programming is a step forward, we can still do better with a more optimal greedy approach that minimizes both time and space complexity. The chosen solution is the optimal greedy approach using 2 pointers. This method stands out for its simplicity and efficiency. The key observation here is that we don't need to explicitly track the entire subsequence. Instead, we only need to keep track of the 2 smallest values, first and second, that could potentially start an increasing triplet. As we traverse the array, we update these 2 values. First holds the smallest number encountered so far, and second holds the smallest number that is greater than first. If we encounter any number larger than second, we can immediately conclude that an increasing triplet exists. This approach operates in linear time, O(n), as it requires only a single pass through the array, and it uses constant space, O(1), as it doesn't rely on any auxiliary data structures. Its efficiency, simplicity, and scalability make it the best choice for solving this problem, especially for large inputs. In this problem, we are tasked with finding an increasing triplet subsequence within an array of integers, nums. Specifically, we need to identify if there exists a triplet of indices I, j, k, such that I less than j less than k and the corresponding values satisfy nums I, nums, j, nums, k. The result is a simple Boolean, true if such a triplet exists, or false if it does not. Now, the first approach to solve this problem is the brute force method. The intuition behind this method is straightforward. We examine every possible triplet in the array and check if it meets the given conditions. For implementation, we use 3 nested loops. The outer loop iterates over the first element of the triplet, denoted by the index I. The middle loop starts from I+1 to handle the second element, j. Finally, the inner loop starts from j+1 to generate the third element, k. By iterating in this structured way, we ensure that we evaluate all valid triplet combinations, satisfying the condition I less than j less than k by design. Once the triplets are generated from the 3 nested loops, the next step is to check their validity. For each combination of indices I, j, k, we confirm if the values at these indices satisfy the conditions nums I, nums, j, and nums, j, nums, k. If both conditions hold, we've successfully identified a valid increasing triplet. At this point, we can immediately return true since the problem only asks if such a triplet exists. However, if no valid triplet is found after fully iterating through all combinations, we conclude that the array does not contain an increasing triplet subsequence and return false. This method, while simple to understand and implement, involves evaluating every possible triplet, which can become computationally expensive as the size of the array increases. Although the brute force method guarantees correctness, it is highly inefficient. The time complexity of this approach is O(n) cubed, where n is the size of the array. This cubic complexity arises because of the 3 nested loops, each iterating through the array. For smaller arrays, this might work fine, but for larger arrays, such as when n is in the order of 10,000, the number of computations quickly becomes impractical. Additionally, there's a significant amount of redundancy in this approach. For instance, once a triplet, I, j, k, fails to meet the conditions, any subsequent triplets with the same I or j are likely to fail as well. This redundancy highlights the inefficiency of brute force and motivates the need for optimization. Furthermore, the constraints provided in the problem often hint at the possibility of more efficient algorithms. For example, achieving linear time complexity, or O(n), is feasible with the right approach, and this is something we'll explore with optimized methods. The brute force approach works directly with the input array, which is a simple data structure allowing random access in constant time. This simplicity is one of its strengths, as it avoids the need for additional storage or auxiliary data structures. However, while the algorithm is straightforward, the inefficiency of its O(n) cubed complexity makes it unsuitable for larger inputs. To address this, we can optimize the solution by leveraging a more sophisticated approach. Instead of iterating over all triplet combinations, we can use 2 variables, often referred to as small and middle, to track potential candidates for the triplet as we traverse the array. The idea is to maintain the smallest and the next smallest values we've encountered so far, making it easier to identify an increasing triplet in a single pass. This optimized method reduces the time complexity to O(n), as it eliminates redundant checks and unnecessary iterations, making it far more practical for handling large input sizes. This Python implementation solves LeetCode problem number 334, increasing triplet subsequence, using an efficient O(n) approach with constant space complexity. The method increasing triplet takes a list of numbers as input. It starts by initializing two variables, first and second, to positive infinity. These variables will help track the smallest and second smallest values in the array. The goal is to find three numbers such that first, second, third. The algorithm iterates through the array using a single loop. For each number, it checks 1. If the number is less than or equal to first, update first to the current number. This ensures first always holds the smallest number encountered so far. 2. If the number is greater than first but less than or equal to second, update second to the current number. This ensures second holds the smallest number greater than first. 3. If the number is greater than both first and second, it means we have found an increasing triplet, first, second, current number, so the function immediately returns true. If the loop completes without finding such a triplet, the function returns false. This ensures that the algorithm efficiently determines the presence of an increasing triplet subsequence in linear time. The code is concise, avoids unnecessary complexity, and handles edge cases like empty arrays or arrays with fewer than 3 elements implicitly by design. This Java implementation mirrors the Python solution, utilizing two variables to track the smallest and second smallest values in the array. The logic iterates through the array, updating these variables as needed, and returns true if a third number satisfying the triplet condition is encountered. Key differences include Java's strong type declarations and the use of integer.max_value to represent infinity. The concise structure ensures optimal readability and performance. To solve the problem, we initialize two variables, first and second, both set to infinity. These will help us track the smallest two numbers in an increasing sequence. Now, let's work through the array nums equals 1, 2, 3, 4, 5. Starting with number equals 1, since 1 is less than or equal to first, we update first to 1. The state becomes first equals 1, second equals inf. Next, for number equals 2, we see that 2 is greater than first but less than or equal to second, so we update second to 2. The state now is first equals 1, second equals 2. Then, with number equals 3, it is greater than second, which means we've found an increasing triplet, 1, 2, 3. At this point, we return true as the output since the condition is satisfied. Now, let's analyze a different example where nums equals 5, 4, 3, 2, 1. Again, we start with first and second set to infinity. For number equals 5, since 5 is less than or equal to first, we update first to 5. The state becomes first equals 5, second equals inf. Then, for number equals 4 is less than or equal to first, so we update first to 4. The state now is first equals 4, second equals inf. Similarly, with number equals 3, it is less than or equal to first, so we update first to 3. The state becomes first equals 3, second equals inf. For number equals 2, since it is less than or equal to first, we update first to 2. The state becomes first equals 2, second equals inf. Finally, with number equals 1, we again update first to 1 because it is less than or equal to first. The state is now first equals 1, second equals inf. Since we never find a number greater than second, no increasing triplet exists in this case, and the output is false. Finally, let's examine nums equals 2, 1, 5, 0, 4, 6. As before, we initialize first and second to infinity. For number equals 2, since it is less than or equal to first, we update first to 2. The state becomes first equals 2, second equals inf. Next, for number equals 1, it is less than or equal to first, so we update first to 1, resulting in the state first equals 1, second equals inf. Then, for number equals 5, it is greater than first and less than or equal to second, so we update second to 5. The state becomes first equals 1, second equals 5. With number equals 0, since it is less than or equal to first, we update first to 0. The state is now first equals 0, second equals 5. For number equals 4, it is greater than first but less than or equal to second, so we update second to 4. Now, the state becomes first equals 0, second equals 4. Finally, for number equals 6, it is greater than second, which means we have found an increasing triplet, 0, 4, 6, thus, we return true as the output. The time complexity of this solution is O, n, where n represents the length of the input array nums. This is because the algorithm processes each element of the array exactly once in a single traversal. Let's break this down step by step. First, we initialize two variables, first and second, and assign them the value of positive infinity. This initialization is a constant time operation, O1. Then, we have a for loop that iterates through the array. During each iteration, we perform up to 3 comparisons or assignments, checking and possibly updating the values of first and second. Each of these operations is constant time, O1. Since the loop runs n times and each iteration is O1, the total time complexity for the loop is O(n). Finally, the return statement at the end of the algorithm executes once and is also O1. When we combine all these components, the initialization and return steps are negligible compared to the loop traversal, so the overall time complexity of the solution remains O(n). The space complexity of this solution is O1, meaning the algorithm requires constant space regardless of the size of the input array. Let's see why. First, the solution uses only 2 auxiliary variables, first and second, to keep track of the smallest and second smallest values encountered so far. These variables occupy a fixed amount of memory, which doesn't grow with the input size. Additionally, the algorithm does not use any extra data structures such as arrays, hash maps, or recursion stacks, which could otherwise increase space usage. Since the memory footprint remains constant and does not depend on the number of elements in the input array, the space complexity of the solution is O1. Now, let's analyze the algorithm in terms of its best, average, and worst-case scenarios. In the best case, the first 3 elements of the array already form an increasing triplet. Here, the algorithm identifies the triplet and terminates early, processing only 3 elements. The time complexity in this case is O1 for the comparisons and a constant number of iterations. For the average case, the algorithm inspects all elements of the array before determining whether an increasing triplet exists. This results in a time complexity of O(n). In the worst case, the array does not contain any increasing triplet, requiring the algorithm to traverse the entire array. Even in this scenario, the time complexity remains O(n), as each element is processed exactly once. Across all these cases, the algorithm consistently exhibits efficient performance within its defined complexity bounds. To understand the efficiency of the current solution, let's compare it to a naive approach. A naive method might involve checking all possible triplets in the array using 3 nested loops, resulting in a time complexity of O(n cubed). Alternatively, using 2 nested loops with a helper array to track the smallest elements would reduce the time complexity to O(n squared, but this approach would still require additional space. In contrast, the current solution uses a greedy single-pass strategy to reduce the time complexity to O(n). It processes each element only once and performs constant time operations during each step. Additionally, the space complexity of the current solution is O(1), as it only uses 2 variables, first and second. This is a significant improvement over naive approaches that might require O(n) space for auxiliary arrays. Mathematically, the total time complexity is O(n), because the algorithm performs a single traversal, and the space complexity is O(1), since no additional memory is used beyond the 2 variables. This makes the current solution optimal in both time and space for solving the problem. When tackling this problem, there are several common pitfalls to watch out for. First, it's important to handle edge cases, such as arrays with fewer than 3 elements. Since the problem requires identifying a triplet, you can immediately return false for these cases to save unnecessary computation. Another frequent issue is misunderstanding the condition that the indices must follow the order I less than j less than k. Some solutions incorrectly assume that the indices can be in any order, which leads to invalid results. Additionally, using a naive triple loop approach with an O(n) cubed time complexity is often inefficient and can result in a time limit exceeded error for larger inputs. Instead, you should aim for optimized solutions that utilize auxiliary data structures or other techniques. Integer overflow is another concern, especially in languages like C++ or Java, where large input arrays may cause issues during comparisons or arithmetic operations. Lastly, selecting appropriate data structures is crucial. For instance, using an unsorted array instead of a binary search tree or a stack can lead to slower or incorrect solutions, so always align your choice of data structure with the problem's requirements. Now, let's focus on insights that often come up in interviews. A key aspect of solving problems like this is recognizing patterns. Many triplet or subsequence problems involve maintaining state as you iterate through the array. The challenge is to efficiently track the smallest and middle elements without losing context. Sometimes, a 2-pass or 3-pass approach can simplify the solution. For example, you might pre-process the array to track minimums from the left and maximums from the right, which can reduce the remaining work to linear time. Space optimization is another common discussion point in interviews. Once you've solved the problem, interviewers might ask how you could reduce auxiliary space usage while keeping the time efficiency intact. Finally, make it a habit to explicitly address edge cases, such as empty arrays, arrays with duplicates, or arrays that are entirely non-increasing. A solid discussion of edge cases demonstrates a thorough understanding of the problem. This problem also connects to a variety of related challenges, which can help you deepen your understanding of similar concepts. For example, LeetCode 300 focuses on finding the longest increasing subsequence, which is a more general version of this problem and often uses comparable state tracking techniques. Another related problem is LeetCode 128, which deals with finding the longest consecutive sequence and requires efficient solutions for subsequence-like scenarios. Of course, LeetCode 334, the increasing triplet subsequence, is the problem we're currently discussing, and it's a common variant that appears in interviews. Finally, LeetCode 673, which asks for the number of longest increasing subsequences, explores counting-based solutions and adds a layer of complexity to state tracking problems. By practicing these related problems, you can build a strong foundation for solving a wide range of subsequence challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is an optimized brute force method. Instead of using 3 nested loops, you can reduce the complexity to O(n) squared by using 2 loops and maintaining the smallest value found so far. While this is faster than the naive approach, it's still inefficient for larger inputs. A better solution involves a single-pass approach with state tracking. Here, you maintain 2 variables, often called first and second, to keep track of the smallest and second smallest elements as you iterate through the array. This method achieves O(n) time and O(1) space, making it the most efficient. However, it requires meticulous implementation to avoid logic errors. Lastly, you could use a binary search tree or an ordered set to dynamically maintain elements. This approach allows for efficient insertion and range queries and achieves O(n) log n time complexity, though it requires additional space for the data structure. Each method has its strengths and weaknesses, so the choice depends on the constraints and requirements of the specific problem. Great job following along. Today, we explored the increasing triplet subsequence problem and learned how to optimize our solution. Remember, practice makes perfect. Keep challenging yourself with similar problems. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!